Okay, so we're going to hit the applications part in this second video, and let's dive right in. I don't mean for this to take as long as it's taking, so I'll try to go sort of quick. Number of tickets purchased by a customer for a musical performance at a certain concert hall can be considered a random variable. Table below shows the relative frequency distribution for the number of tickets purchased by a customer. Number of tickets, let's just call that X. Relative frequency, we'll call that P of X, and the question is, suppose each ticket for a certain musical performance costs $12. Based on the distribution shown, what is the mean, so we're looking for a mean, cost per customer for the performance? Well, this is only going to give us an average number of tickets, but if we can get that and multiply it times this $12 per ticket, that should give us the average cost per customer for the performance, because that's kind of a linear transformation. So let's just say we have mu of X, and you can do this on your calculator, but the long way would be 1 times 0.20 plus 2 times 0.45. All right, having similar issues to what we had the other day. 0.45 plus 3 times 0.10 plus 4 times 0.20 plus 5 times 0.05, and if you do all that math out, you're going to end up with $2.45 tickets rather, and that's per person who buys the tickets. And so all we need to do is multiply that by 12, so 2.45 times tickets times $12 a ticket is $29.40. All right, and so that's going to be letter D. Okay, so there's your first one. All right, in a certain card game, the player is awarded 5 points, so that's an award, that's an additional amount, a good amount, for each card that is moved to a correct position. A player is penalized, and that's a deduction, so we'll make that kind of like a minus. 10 points for each minute the game is played. Let the random variable be X represent the number of cards and move to the correct position, and let the random variable Y represent the number of minutes the game is played. So that'll be minutes. And we have the average of each one. There's your means and standard deviations and everything in your table. All right, assume that X and Y are independent. What is the expected value and the standard deviation of the points per game? All right, so we can convert cards and minutes into points added, points subtracted, and come up with some kind of a mean for the points. All right, so we're really looking for this, mu of 5x minus 10y. All right, yeah. So that's the difference of the mean of a difference is just the difference of a mean. This will be mu 5x minus mu 10y. All right, and so all we have to do is convert these from means for cards and minutes to points. All right, so this is just going to be equal to, we'll write it down here, 9.5 times 5 points for an average number of cards moved to a correct position, minus 5.4 times 10. So there's a 10-point deduction per card, per minute, and that'll be 5.4 minutes. And when you get that done, this will give you negative 6.5, which means the game really isn't in this player's favor. So it could be A or B, so C, D, and E will be out. And getting the expected value or the mean is usually pretty easy. It's the standard deviation that may not be quite so easy, all right? So we need sigma of 5x minus 10y, okay? So we're going to have to change the original standard deviations into, instead of cards and minutes, we're going to change them into points. And then the minus can never be a minus when we combine these things because spread always adds, all right? So in order to get this right, because I did it a few times and it just seemed to get crazy when I tried to do it all at once, was that I went ahead and did just the mean of the standard deviation of 5x. And so that's your original standard deviation times 5, right? So 12.9 times 5. Now you could square both and take the square root, but that's just digging a hole and filling it back up. All right, so this will be 64.5, and that will be the standard deviation of 5 times x. And then we need the standard deviation of 10y, which will just be 10 times 1.1. And that'll be 11. Now these are standard deviations. To add those up, we have to go to variance. So let's just say that the standard deviation of 5x minus 10y is going to be the square root of 64.5 squared plus, remember, minuses always turn out to be pluses, 11 squared. And so you end up with 65.4313. And they just round it to 65.4, so that's your correct answer. Okay? So, yeah, there is some transformations and some combinations in the same problem. All right, so number 3, random variable x is normally distributed with a mean of 5 and a standard deviation of 25. The random variable y takes your random variable x and multiplies it times 4 and adds 2. So you don't really need to know if it's normal. You don't need to know if this stays normal. We're just going to use rules for means and standard deviations. Okay? So to get y, we're just going to take the original mean, which is 5. So let's go ahead and call this mu of 2 plus 4x, and that'll be your mean for y. So that'll be 5 times 4 plus 2 is 22. All right, so that takes that out and that takes that out. All right, so now we need sigma of 2 plus 4x. And remember that the multiplying part will dilate your spread, but the additive part just shifts it left and right on a horizontal axis, which means that the shape of it won't change. So you don't need the 2. That's the A part that really isn't necessary. Okay, so pretty much this is just going to be 4 times the original standard deviation, which is 25, and that'll give you 100. If you are, just doing a transformation on a standard deviation without trying to combine it with a second standard deviation, you don't need to square and then undo it with the square root, because it's like, again, digging a hole and filling it back up. So that would give us this. That is our answer for this. Okay? So I got to switch over to the next sheet, so stand by. All right, so question number 4 is probably going to be the toughest one that we have here. Not all of it. So when you get a multi-part question like this in FRQ, which, by the way, that's all that this year's test is going to be, we just need to get as many points as we can. So we have a shopping mall has 3 automated teller machines. Because the machines receive heavy use, they sometimes stop working and need to be repaired. So the random variable x represents the number of ATMs that are working when the mall opens on a randomly selected day. So this is x. Here's p of x. And the table shows the probability distribution. So what is the probability that at least one ATM is working? Remember that at least one, probability of at least 1 equals 1 minus the probability of none. All right, that's an important thing. I'm glad it showed up here. So this will be 1 minus, none is 0, which is 0.15, and that will give you 0.85. Now you could have just added those 3 up and gotten the same thing. It's totally up to you however you want to do it. But it's nice to see this in a review. So what is the expected number of ATMs that are working when the mall opens? That's mu of x or e of x, however you want to put the notation. So that's 0 times 0.15 plus 1 times 0.21 plus 2 times 0.40 plus 3 times 0.24, and that'll give it to you. You can do that on the calculator instead of doing it this way. You should either way get 1.73 ATMs. So close to 2 would be expected to be opened on any given day. All right, this is going to be kind of rough. D might be a little rough too, but let me see if I can help you figure it out. All right, so what is the probability that all 3 ATMs are working when the mall opens, given that at least one ATM is working? Okay, well, this is going to be the probability of that we get x is equal to 3, given that x is greater than or equal to 1. All right, and wow, that looks kind of rough. What I would like for you to remember, though, is remember we had the probability of B given that A occurred, and that was just the probability of A and B divided by whatever this is. That's the probability of A. We learned that yesterday. Right. So let's look at it, or maybe it was Monday that we learned it. Either way. So we're going to expand this the same way. We'll just kind of call this B and this A. So we'll get the probability that x equals 3 and that x is greater than or equal to 1 divided by this right here, probability that x is greater than or equal to 1. All right, now the one thing you don't want to do is multiply those two together and assume that the two things are independent. Because if I tell you that at least one of these are working, 1, 2, or 3, you have some idea that it might be 3, so those are not independent. So what we want here, and this is kind of bizarre, we've never really run into this before, is we want the intersection. Because isn't and considered to be an intersection? All right, so here is at least one working. And let me change colors. Here is 3 working. And that did not change colors. Yay me. All right, get that red. Okay, do you see where they are intersected? Right here. So basically, that numerator is just merely the probability that x equals 3. And we already know the probability that x is greater than or equal to 1 because that's this. All right, so probability that x is greater than or equal to 1. So we have 0.24 over 0.85, which gives you 0.282. And I understand that that might be tough to get, but it came from an old AP exam, so it could be on another one. All right, last one. Given that at least one ATM is working when the mall opens, would the expected value of the number of ATMs that are working be less than, equal to, or greater than the expected value from part B? All right, this is the expected value from part B. And they're asking if they're saying that at least one ATM is working, that means that this is no longer valid. This becomes impossible, right? Because they already said at least one is working. Well, the question becomes, what happens to that probability? It can't just vanish. It's going to have to go over to here and somehow spread itself out among these 3. Well, if you spread that out and make those probabilities bigger, it's going to make the products bigger and they will add up to a bigger expected value. So that's a little hard to put into words, so I'll give it a shot. So it should, wow, that's terrible. Let's try that again. It should be more because if x equals 0 can't happen, then its probability would have to be distributed among the other three outcomes. Among the other three outcomes. Making the expected value bigger. All right, so there's that. Interesting question, really. They kind of dropped the random variable approach and changed it into just straight probability. All right, I'm going to go down to 6, and then we'll finish up with 5. All right, random variable x has a mean of 120 and a standard deviation of 5. Random variable y has a mean of 100 and a standard deviation of 9. If x and y are independent, approximately what is the standard deviation of x minus y? All right, sigma of x minus y. All right, these are being combined with subtraction. That means that it will be an addition, and you have to go through variance when it's two random variables. So that would just be 15 squared for the first one, and 100, I'm sorry, that would be 9. I misread it. Let me get that off of there. Plus 9 squared, and that would be the square root of 225 plus 81, and that'll give you 17.5. So it's B. All right, now the final one doesn't really end up being a random variable. It just seemed to kind of look that way when I put it here, but I kind of like it, so I'm going to go ahead and just cover it. It says the prices in thousands of dollars of 35 used cars at a certain car dealership are shown in the table below. Which of the following best describes the shape of the distribution? All right, so this again is sort of a weighted situation, but it's more like what we did in chapter 1 with just data and histograms and whatnot. But what I want you to see is that your frequency, or the counts, really do pile up in the low end, right? 4, 6, 7, 6, and then they kind of spread out going to the right. That should be skewed to the right. Now, if that doesn't occur to you and you kind of want to look at it in your calculator, I put the data in there. So here is P for the price, here's frequency, and I put them all in. You're welcome to pause if you want to do this with me or just watch. All right, so I'm just going to go ahead and make a probability histogram out of this. So it'll be menu, and oh, that's not what I want. Let's go ahead to the home screen and go to a stats graph, and we want price on the horizontal. Now don't put anything in the vertical because you'll just get this weird pattern of dots. Just go to menu and plot properties, and we want to add a Y summary list. And that's what we want for the variable will be the frequency. And there it is. See the skew to the right? So I believe that answers the question. All right, I've had your attention probably far longer than I should. I hope that this was useful to you, and yeah, these are going to be, I think, a big part of your AP exam, random variables. I just have that feeling. So hopefully along the way I can get you more problems to work on, or you can find them all throughout the practice exams that I posted. So on that note, I'm going to close out, and I will see you tomorrow.